Architecture affects us much more immediately than many other art forms because of the prominent position it has in our lives. Put simply, architecture is three-dimensional art and design that surrounds and influences us. We live in works of architecture, learn in them, shop in them, and more. Architecture satisfies the basic human need of shelter, symbolizes safety and security, and suggests feelings of permanence and place. Architecture also reflects human development. Historical buildings connect us to history by showing us how people lived in the past, while new buildings reflect innovation and progression. Architecture is primarily concerned with three things: structure, function, and form. Structure refers to the engineering or structural integrity of the building. The primary goal of an engineer or an architect is to understand and control the forces that are pushing and pulling on the structure of the building. These forces are called stresses or sometimes loads, and they are constantly at work. They include things like the building's own weight and the force of gravity. These are permanent and unchanging stresses, but there are also temporary or changing stresses like the weight of people or furnishings inside the structure, the force of the wind against the structure, or maybe the weight of a big load of snow on top of the roof. Architects and engineers use different structural systems to channel the stresses that act upon the building down to the ground. When stresses pull, they cause tension, which lengthens and stretches the materials of the building. When stresses push, this causes compression, which squishes and shortens the materials. There are two basic families of structural systems: shell or load-bearing construction, in which the building materials provide the structural support as well as the visible exterior covering, such as at the Great Pyramids of Giza, which were built of carefully stacked sandstone blocks that had been faced with white limestone. The largest of the three pyramids at Giza is the Pyramid of Khufu, which contains an estimated 2,300,000 blocks of stone, calculated to weigh an average of 2.5 tons each. Most, although not all, ancient architecture tends to fall within this shell or load-bearing construction system. The other type, or the other main family of construction systems, is generally referred to as skeleton and skin construction because the structure, much like the human body, consists of a rigid skeletal support system that serves as the basic framework, with a lighter weight, often more visually appealing skin that serves as the covering. One of the most straightforward examples of skeleton and skin construction are teepees used by Native Americans on the plains. Teepees typically consist of a stable conical framework made out of 3 to 4 long poles with an additional 20 to 40 smaller poles that fill out the oval floor shape and hold up the hide or the canvas walls. The choice of which structural system to use is affected by a number of variables, but it's often dependent on the availability, cost, and character of building materials. Different types of building materials have different levels of both tensile and compressive strength, meaning each material resists the stresses of tension and compression differently. For example, both stone and concrete have great compressive strength, so they can withstand a lot of compression, but they have very little tensile strength, so they are susceptible to collapse under tension. Architects and engineers measure the strength of a material so that they can anticipate and control the balance of forces at work. If balanced correctly, a building might last for thousands of years, but if not, it might collapse. Architectural space is also the result of thoughtful design which reflects the building's function and its intended role in the community. The architect must also collect and consider information about the planned location of a building, its place within the community, neighborhood, or city, and its intended purpose. This information not only helps the architect choose what structural materials or systems to use, it also informs the building's design so that it can be both efficiently functional and visually appealing. For example, in the late 15th, early 16th century, the Turkish architect Sinan was the chief architect to the Ottoman court under Sultan Suleiman. Sinan was commissioned to design this magnificent royal mosque, and it was his understanding of architectural principles and his ingenuity that really allowed him to develop new ways of opening up architectural spaces and to create this masterpiece, which includes a central dome with 4 surrounding half domes. The design here perfectly balances all of the individual parts and has enabled this structure to remain standing for over 500 years. The many windows allow natural light to stream in and illuminate the upper portion of the domes, drawing the worshippers' attention upward as if toward the heavens, symbolically supporting the building's intended function as an awe-inspiring place of religious worship. So again, most, although not all, ancient architecture falls within this load-bearing construction or shell construction category. This is largely because ancient cultures relied on building materials that came from the earth, such as stone, wood, and clay. These materials are plentiful, but they must be altered and applied carefully in order to create lasting architecture. One of the most basic forms of load-bearing construction, and probably the most direct way of building something, is stacking or piling materials on top of one another. Again, such as at the Great Pyramids of Giza, or as in this Maya pyramid from the Great Plaza in Tikal, Guatemala, which was constructed between about 300 and 900 CE. Maya pyramids primarily served as platforms for temples, which is what that uppermost structure is there. And this is just one of hundreds of such pyramids that protrude from the rainforest in Guatemala, sort of rising sharply toward the sky, really emphasizing the structure's role as a gateway to the gods. Each layer of stones here kind of bears down on the layer beneath it, holding all of the individual stones securely in place, creating a perfectly symmetrical work of monumental architecture that has truly withstood the test of time. Another example of monumental load-bearing construction created from simple earthen materials stacked atop one another is the great mosque in the town of Djenné in the country of Mali in West Africa. The design and execution of this building reflects the architect's consideration of available materials, the building's location, and the structure's intended function. Djenné has long been a trade center and site of Islamic learning and pilgrimage. The Great Mosque is located next to the town's huge, bustling marketplace. The original mosque structure on this site was converted from the king's palace when he converted to Islam in the 13th century, but in the 19th century, that structure was demolished and replaced with a smaller, more modest building. The current structure that we see in this photograph was completed in 1907, and it is designed after that original 13th century version. This is considered the largest mud brick structure in the world. A mixture of mud, water, and straw was collected and packed into a mold and then left out in the sun to dry. The dried mud bricks were then stacked to form the structural walls and then covered with a mud plaster to help hold them in place and to give a plastic sculptural quality to the imposing structure. Numerous palmwood beams support the mosque and line the ceiling, giving it a distinctive look, but also serving functional purposes. Some beams structurally support the ceiling, but those that protrude from the exterior are used to access the walls for annual maintenance. Because mud bricks are natural materials, they are vulnerable to the elements and will disintegrate over time. Each year, the city of Djenné hosts a festival during which all of the citizens of the city contribute to the replastering of the mosque's exterior to repair melting and cracking caused by seasonal rains. The region's hot climate also affected the building's design. The mud bricks absorb heat to keep the interior cool during the day, and then they release the heat at night, keeping the interior warm. Additional roof ventilation also helps to cool the interior of the building, and you can sort of see those ventilation systems here, these sort of mounds with holes in the top that can allow the hot air to escape, or in this photograph, those holes have been covered by small ceramic dishes to sort of keep that warmer air inside. The mud brick and palm wood structure here is quite typical of many West African architectural practices, but the design of the Great Mosque also incorporates characteristics of Islamic mosques. The three rectangular towers across the facade or the face of the mosque are minarets, which are traditionally used to call the faithful to prayer. Spiral staircases inside those minarets lead to the roof, which features a cone-shaped spire topped with an ostrich egg. These eggs are important symbols of fertility and purity for the people of Jenne. The interior prayer hall of the mosque is what we call a hypostyle hall, a large interior room created by using a series of columns, in this case mud brick columns, to support a flat ceiling. Here, the mud brick ceiling is further supported by those palm wood beams. The hypostyle hall is very typical of most Islamic mosques because it provides a spacious interior setting that can easily be expanded to accommodate a growing congregation, and worshipers can also easily organize themselves within the prayer hall according to those rows of columns. While stacking and piling can produce monumental structures that can withstand the test of time, it really only provides small, dark interior spaces, if any at all. To create an interior space, an architect needs to create a span or a distance between two supports within a structure. One of the most basic, ancient, and effective ways of doing this is through post and lintel construction, which consists of a horizontal beam or lintel supported by an upright post at each end. Gravity pushes down in the center of the lintel where it's unsupported, so the distance that the lintel can span is determined in part by the material. For example, stone and wood are the two most common materials for this type of load-bearing construction. However, neither has just a great amount of tensile strength, so the larger the distance of the span means a greater risk of cracking or collapse. Additionally, the size and number of upright posts utilized also determines the overall height and width of this kind of architectural space. Ancient Egyptian architects built the Temple of Amun-Ra at Karnak by placing a series of post and lintel spans side by side to create a spacious interior, like what we can sort of see here in this photograph of the Great Court. This temple complex also included a hypostyle hall, which again is a large interior room created using a series of columns, which is also called a colonnade. And so that's used to support a flat ceiling. In this case, the hypostyle hall was used by Egyptian priests for rituals to worship the god Amun-Ra, while ordinary people worshipped in the open courtyard outside. Ancient Greek architects adapted this Egyptian system and went on to become some of history's greatest practitioners of post and lintel construction. First, they standardized the basic post or column, an essential point of compression used to support a building's weight. Classical Greek architecture is dominated by the use of columns, which, as a structural element, consist of three parts: a capital or uppermost part, which serves as the transition between the lintel and the main vertical section or shaft of the column, which rests on a base that serves as a stabilizing point where the building's weight is concentrated. There are three different column styles which help us to identify the three different architectural orders of ancient Greece. We have Doric columns, which have a sort of plain, round capital and no base. Ionic columns, these have sort of a scrolling formation called a volute on their capital, and they do tend to have a base. And then Corinthian columns are the most decorative, and they have a leafy capital which is modeled after the acanthus plant, and they tend to have a base as well. In the photo on the right here, we have the Temple of Athena Nike on the Athenian Acropolis, which is a great example of ancient Greek architecture that uses this standardized post and lintel system. This was constructed between about 421 and 415 BCE by the architect Callicrates to house an important statue of Athena, the patron goddess of the city. Notice the side and rear walls here are typical kind of load-bearing construction, and they consist of stacked stones, stacked cut stones, I should say. But then the front, or the porch here, the facade, it has, or rather it uses, post and lintel construction. We have these 4 Ionic columns, which we can tell they are Ionic columns because they have these scrolling volute capitals here. But they support this one long horizontal lintel. And so ancient Greek architecture like this really made a lasting impact on Western architectural traditions. The Romans very quickly adapted Greek styles and added their own architectural elements. Rome's innovations then influenced later styles of architecture in the Renaissance and Baroque, so during the 15th, 16th, and 17th centuries in Europe. For example, on the left here, we have the Tempietto of San Pietro in Rome, which was designed and constructed by one of the great architects of the High Renaissance, Donato Bramante. And then this sort of style was revived again in the 18th and 19th centuries, again, primarily in Europe, with what we call the neoclassical or new classical architecture, an example of which can be seen in Lord Burlington's Chiswick House in London. This classical or neoclassical style was and is still primarily used to celebrate and reflect the ideals of democracy that the ancient Greeks instituted in order to allow free citizens in Athens to decide their own destiny. So we often see this style, especially in the United States and France, being used in government buildings, but it has also sometimes been used in domestic architecture as well, again, such as this Chiswick house. So again, the primary limitation of the post and lintel construction system is that lintels cannot span large distances. Ancient Babylonians in Mesopotamia and the Mycenaeans of early Greece both solved this issue with the corbeled arch. Corbeling is the stepping inward of successive layers of cantilevered materials. That is, materials that are secured at one end while the other protrudes out over empty space. That's what cantilevered means. This sort of successive stepping inward of layers of stone over a doorway allows for the compression created by the weight of the building to be directed outward through those cantilevered stones and then downward through the upright posts or the load-bearing walls, rather than acting straight downward on the unsupported center of the lintel. This process or this system really reduces the pressure on the structure and allows the architect to span a larger distance. For example, we're looking at, on the right side here, the entryway to the Mycenaean tomb of Agamemnon, which is also sometimes called the Treasury of Atreus, which was constructed around 1250 BCE, and it really shows this ancient corbelled arch construction. Here we have a lintel that sort of interrupts the space between the doorway and the arch that's been created by that progressive cantilevering of stones. The lintel, it sort of provides additional support, and then that arch really allows for a wider span. And then as you can see in these images, that arch also brings more light into the chamber beyond, which is itself a sort of spacious corbelled dome or vaulted space, again created by layers of cantilevered stones. In this case, on the exterior, I don't have a great photo, but on the exterior, earth or dirt has been kind of packed over that vaulted stone to help hold those stones in place. So from the exterior, this kind of looks just like a hill. The ancient Romans then fully developed and perfected the rounded arch, which is much more efficient than the corbelled arch at distributing compressive stress over the whole of the structure by spreading the weight of the building outward along the entire span of the arc. This really allowed the Romans to design and construct wider spaces than ever before. However, channeling the weight of the building along the arc also creates an outward thrust, or a sort of outward pushing force that must be stopped by a heavy support or buttress. The wider the span of the arch, the greater the outward thrust, and therefore the bigger the posts or the supports of the arch must be. In a true rounded arch, which is also sometimes called a Roman arch, each stone exerts equal pressure on the next, so they hold each other in place. And that's true in the structure of the Pont du Gard in southern France. This was constructed in the 1st century. In the upper level here is an ancient Roman aqueduct that was built to move fresh water over 30 miles from mountain springs to populated areas that had recently been conquered by Rome. Each arch consists of perfectly cut stones that fit together and again support the weight of the next, and then so each arch helps to support the next one in the series. To create a sort of consistent downhill path for the water to flow, the aqueduct tapers at a rate of about 1 inch down for every 33 inches along. Structures like these really benefited the local community, projected Roman imperial power, and enabled the army to move quickly across their new territory. This structure is truly a testament to the durability of the round arch. The lower bridge portion here is still in good enough shape to be used today, and it's part of the bicyclists' route during the Tour de France. After perfecting the round arch, Romans developed the vault, which is essentially an arch that has been elongated or stretched into a long hallway to create a more spacious interior. The most common type of vault, the barrel vault, is a long semicircular arch. Although developed by the ancient Romans, the barrel vault was especially important during the European Middle Ages, particularly between about 1050 and 1200, when churches had become significant centers of community activity and needed to expand to accommodate larger crowds. The term Romanesque, which means in the Roman manner, was coined in the 18th or 19th century to refer to the style of architecture built in Europe during this time, particularly in European churches during this time, that was inspired by imperial Roman buildings. Romanesque churches feature solid masonry walls, huge rounded arches and barrel vaults, and you can kind of see that in this photo on the right here, which shows the Church of St. Madeleine at Vézelay, France. This was constructed in the 12th century. So the use of stone barrel vaults really creates a more spacious interior, both horizontally and vertically there. But it also helped with fire control and weather resistance, as earlier churches had typically had stone walls, but they had thatch or wooden roofs, which are, of course, subject to decay and highly flammable. However, because the weight of the vault thrusts outward, the walls supporting it must be quite massive so as to avoid collapse. Vaulted side aisles, which you can sort of see in this photograph, were used to help counteract this outward pressure and support both sides of that central vaulted space, which is called a nave. These side aisles consist of a series of groin vaults, or areas where two barrel vaults intersect at right angles. With a groin vault, the weight or stress is channeled down to those supportive buttresses, which are in each of the four corners, really opening up even more space than a barrel vault. These groin vaults, which are accessed through these round arches along the sides, divide those side aisles into bays. And then the singular central barrel vault really helps to unify the entire space, while the repetition of arches and bays within the aisles creates this sense of rhythm that is then further enhanced by these repeated transverse arches, which that is this sort of extra stone that's been placed kind of throughout the vault here, which provides additional strength and gives the surface of the wall and the ceiling a bit more sculptural form. So because the walls had to be massive to support the weight of the vault's outward thrust, typical Romanesque churches could only have a few very small windows, resulting in very dark, kind of gloomy interior spaces. One particular church leader, Abbot Suger, at the Abbey Church of Saint Denis near Paris, France, he was very highly unsatisfied with this kind of gloomy austerity, and he sought instead to create a space in which worshippers were bathed in divine light and could feel lifted towards the heavens. He redesigned the existing Romanesque structure using a few crucial innovations. First, Suger observed that the rounded arch and barrel vault of Romanesque churches tended to appear squat and heavy, and he instead wanted an arch that would raise the worshipper's gaze upward towards heaven. He achieved this with pointed arches and pointed vaults, which are seemingly not all that different from the traditional rounded versions. However, by adding a point to the arch, the weight of the building is channeled outward and downward along a steeper angle and therefore at a greater rate, while the sharp apex of this point also has a strong upward visual emphasis. Because the stress is channeled at a greater rate, pointed arches and vaults in general can be taller and span greater distances than their rounded counterparts. Suger also wanted to incorporate more natural light in the interior space. However, adding larger windows would also weaken the walls and increase the chance of collapse. To solve this problem, he added thick external support columns, or buttresses, along the bases of the outer walls, and then he incorporated a new architectural structure called the flying buttress, which is essentially a sort of arch or attachment on the exterior of a building that transfers some of the weight of the vault kind of outward beyond its own walls to that exterior support or buttress. So with these additions, those central walls no longer needed to bear all of the weight of the building, so the number and size of windows could be greatly increased, and therefore much more natural light could be allowed into the interior space. Suger then took things a step further by incorporating large-scale stained glass windows, so the natural light would pass through these huge multicolor images that were based on biblical narratives, projecting Suger's desired divine light onto the worshippers. Suger's innovations here, including the use of the pointed arch and vault, the addition of those external buttresses, particularly the flying buttresses, and the increase in number and size of windows, and the use of stained glass, all of these things were very pivotal in the development of a highly influential architectural style, which we now know as the Gothic style. Another architectural element that stems from the development of arches and vaults, and that was also perfected by the ancient Romans, is the dome. A traditional hemispherical dome is essentially a rounded arch that has been rotated 360 degrees on its vertical axis. Domes are very strong structures and can span large areas because, like the arch or the vault, its weight is dispersed outward toward the walls. Most dome constructions require the support of very thick walls. For example, the Roman Pantheon, which was constructed between about 118 and 125 CE, is a spectacular example of architecture from the Roman Empire. The name Pantheon translates to Temple of All the Gods. However, research indicates it was originally associated with the divine authority of Roman emperors. The facade or face of the structure looks like a classical Greek temple with Corinthian columns that support a horizontal lintel. But once inside, you find yourself in a huge cylindrical drum or rotunda, a round room, that has been topped with an enormous hemispherical dome with an oculus or opening in the center. At its apex, the dome is 143 feet from the ground, and the drum is 143 feet in diameter. So a perfect sphere could fit within this space. The construction of this dome was made possible by the Romans' revolutionary use of concrete and their engineering genius. As you can sort of see in this little illustration down here, the concrete walls of the drum are quite thick. They are about 20 feet thick. And then the dome itself is thicker along the base where it meets the top of the wall, and it gradually becomes thinner as it moves upward and reaches the oculus, reducing the weight of the dome as much as possible. The interior of the dome is coffered, meaning it has these sort of recessed rectangular panels. And this is a decorative or aesthetic kind of choice, but it also helps to further reduce the weight of the dome by removing additional material. The oculus in the top there allows natural light into the space, and one might tell the season and time of day from where the sunlight hits the interior. Any rain that comes in through the oculus quickly runs off into a drain because the entire floor of the space kind of gradually slopes downward toward the edges. So at the Pantheon, a round dome is paired with a round building, making for a simple, natural connection. However, how might a dome be attached to, say, a square building? Well, this is the case at Hagia Sophia, which was originally built as a church in 6th century Constantinople, the then capital city of the Byzantine Empire, which is modern-day Istanbul, Turkey. Designed by two mathematicians, Anthemius of Traus and Isidorus of Miletus, the dome of Hagia Sophia was the largest interior space of any cathedral in the world for nearly 1,000 years. Each wall of that central square structure, so this structure here, which we can see the interior of on the right side here, each wall contains a huge rounded arch that meets and supports the base of that circular dome. Then we have these curving triangular pieces in the corners. These are called pendentives, and they connect and create a smooth transition between the circular dome and the square room below it. They also help transfer the dome's weight onto these four kind of massive corner pillars, which on the left image you can kind of see the exterior buttressing around those four corners. The inside of this structure is really illuminated by this series of windows around the lower portion of the dome. And these create a sense of rhythm, and then when the light kind of streams in, they sort of make the dome appear to float above the structure and create this sort of mystical or heavenly effect. Interestingly, while this structure was originally built as a Christian church, it was converted to an Islamic mosque when the Turks conquered Constantinople in the 15th century, and that's when these four minarets were added to the corners of the grounds. And then later, in the 20th century, Hagia Sophia was converted to a secular museum. Post and beam construction has been used to build some of the world's finest and oldest wooden architecture. Two of the oldest wooden buildings in the world are on the grounds of the Buddhist Hori Temple in Nara, Japan. This complex, which was originally constructed in the 7th century, utilized a complex post and beam system that is beautiful and structurally sound. Now, this post and beam system was first developed in about the 2nd century BCE in China, right around the same time that the ancient Greeks were perfecting their stone post and lintel construction. But the post and beam was then adopted by Japan by about the 6th century. This system consists of crossbeams and counterbeams, which create a series of layers supporting a very elaborate kind of curved roof. Oftentimes, this curved roof sort of seems to float because it's seated upon such slender supports. An intricate system of interlocking brackets crowns each column, helping to distribute the weight of the roof and large overhanging eaves evenly onto the wooden columns, allowing each one to bear up to 5 times more weight. The main building of the complex, the condo, is a treasure house, and it is almost 61 feet long by about 50 feet wide, while the Gojo no To, or the 5-story pagoda, is 122 feet tall. So this post and beam system is rather versatile, and it can create quite large structures. However, in this case, the pagoda's height was designed to be impressive rather than practical or functional, because you are actually not able to enter the top 4 floors of the structure. So by the 19th century, load-bearing construction systems in which the building's materials provide both the structural support and the exterior covering began to be replaced with skeleton and skin systems in which a rigid skeletal support system serves as the basic framework for a lighter weight skin-like covering in both grand and smaller architectural examples. One of the first examples of this occurred in Chicago in about 1832 with the development of balloon frame construction. Balloon framing involves building a wooden framework by nailing sturdy but lightweight boards together. The builder would then add a roof and cover the walls in clapboard, panels, stucco, really whatever. And so on the right here, we have an example of a domestic architectural style called the stick style, which kind of took advantage of balloon framing to support a very decorative design that often used asymmetry with steep roofs to create a dynamic visual statement. Originally, balloon framing was a sort of derogatory term used by builders who stuck to more traditional building methods and thought the new method was too fragile to support a building, and that the framework would burst under pressure, kind of like a balloon filled with too much air. However, this is still the most common type of domestic construction in the United States and in many areas in the Western world. As a material, iron has been available to humanity since ancient times, and in a molten state, it can be molded or cast into almost any shape. However, it really wasn't until the 18th century that it could be smelted in large enough quantities to play a significant role in construction. An important early example of cast iron construction is the Crystal Palace, designed by Joseph Paxton for the Great Exhibition of 1851 in London. This event was meant to promote trade and showcase Great Britain's goods, services, and technical innovations. Paxton's temporary structure would house the exhibition, and so he wanted it to be just as modern and innovative as the items inside. Paxton was an experienced greenhouse designer, and this informed the design of his Crystal Palace. The walls and roof of the building were made of glass panels supported by a skeletal cast iron structure. The building was in total more than 1/3 of a mile long, and the central vault reached almost 130 feet high. Using prefabricated materials, including cast iron beams and wooden supports, the structure was completed in only 8 months by just 2,000 people. In total, the Crystal Palace utilized about 4,500 tons of cast iron and 990,000 square feet of glass, and it paved the way from 19th to 20th century architecture by demonstrating that so long as the skeleton was firm, the skin could be lightweight and completely non-load bearing, and you could still create a very spacious interior. Although the structure was originally intended as a temporary thing for the exhibition, the Crystal Palace was so well received that it was eventually dismantled and then reassembled in South London, where it served as an exhibition and concert hall until it was unfortunately destroyed by a fire in 1936. By the late 19th century, engineers had figured out that by adding carbon to iron, they could create steel, an even stronger, more rigid metal that opened up even more possibilities for architects. By the 1880s, modern cities were truly in desperate need of new buildings for industry, commerce, and living. However, the rapidly rising cost of urban land deterred new construction. Steel frame construction, in combination with the new invention of the elevator, allowed architects of the late 19th century to build upwards rather than outwards, and the modern skyscraper was born. One of the first architects to note the advantages of steel was Louis Sullivan, a pioneer of skyscraper design. One of his earliest skyscraper designs is the Wainwright Building in St. Louis, Missouri, a 10-story office building and one of the world's oldest skyscrapers. The structure is supported by a steel cage and covered in a terracotta masonry skin. Sullivan argued that form must ever follow function, meaning that the design of a structure should promote functionality and reflect its intended purpose. In his 1896 treatise titled The Tall Office Building Artistically Considered, Sullivan explained that the ideal skyscraper should have three basic sections. The lowest section at ground level should be reserved for businesses that require easy street access, lots of light, and open spaces. These areas usually had access to the basement, and often they were connected to the second floor for additional storage. And then above them, we have this central section, kind of the tallest section of the skyscraper, which may consist of however many stories of offices, all of which are identical in design because they perform the same function. Finally, we have the top attic section, which serves as additional storage and houses the elevator mechanism. On the exterior, Sullivan argued that the attic section should have a distinct cornice or decorative protruding ledge to help individualize the building and to add visual interest. Sullivan's skyscraper designs tended to reflect the elements of a column. The top attic section, kind of with its decorative cornice, sort of reflects the capital of a column. Then we have the middle and tallest section that kind of reflects the column shaft with its strong vertical emphasis. And then the lower section with very little ornamentation reflects the base of a column. Later modernist architects realized that since the steel frame bears the full load of the building, the entire wall could be made of glass. One prominent architect who capitalized on this was Ludwig Mies van der Rohe, who, after fleeing Nazi Germany, settled in the United States. In the 1950s, he partnered with Philip Johnson to design the Seagram Building in New York City, which is the epitome of the modern skyscraper as we know it. Essentially, it is a rectilinear glass tower that has sort of come to personify the standardization and impersonality of the corporate post-war period. The design here is highly efficient in terms of building materials and methods, and it created the maximum amount of office space on a very small urban lot. Mies van der Rohe was criticized at the time for his rather unadorned glass design. However, he argued less is more and proclaimed that God is in the details. After World War I, increased international communications between architects resulted in the development of a common formal language or architectural style that has become known as the international style, and this really emerged first in the 1920s and 30s. International style architects, including Mies van der Rohe, designed structures characterized by the use of modern building materials such as steel and industrial glass to create simplified cubic forms with open interior spaces. This style claimed its rational approach to architectural design could and should be used universally for rich and poor alike. Many of these architects agreed with Mies van der Rohe's idea that less is more, so the international style is also characterized by a lack of ornamentation or decoration. As an example, here we have a design by the Swiss architect Le Corbusier, who argued that a building should be a machine for living in. He said it should be designed as rationally and functionally as any other machine, and it should be designed based on the lifestyle of its occupants. His Villa Savoy in France, which was a weekend home, was designed inexpensively using the international style. The highly geometric structure includes a main floor, which has been constructed of reinforced concrete, or concrete that has been inlaid with steel rebars or fiberglass rods to provide additional reinforcement and help prevent cracking. Here, that main structure has been elevated on slender posts, which creates a covered outdoor space. The exterior is unadorned with this sort of long ribbon window that runs the length of the building, allowing inhabitants to view nature from a very comfortable vantage point. The interior is quite spacious, and it includes movable curtain walls that allow for maximum flexibility according to the functional needs of the inhabitants. And then flat rooftops are transformed into terraces that provide even more functional space. Other modern architects, such as the prominent American architect Frank Lloyd Wright, capitalized on new materials like steel, glass, and reinforced concrete, but unlike international-style architects, Wright argued that a building should become part of its natural surroundings. Where Le Corbusier argued a structure should be a machine for living, Wright believed a structure's design should respond organically to its location. The best example of this belief is Wright's Falling Water in Bear Run, Pennsylvania, which was completed in 1939 as a weekend or summer home for the family of Edgar Kaufman. Wright designed the home so that, rather than sitting atop the landscape, the structure would be sort of integrated within it. Falling Water sits on top of this stream and waterfall that flows into a natural pool that the Kaufman family visited in the summertime and went swimming in. The main portion of the structure sits on top of a naturally cantilevered stone, which then is echoed by these cantilevered terraces made out of reinforced concrete. These project outward from the core up to 18 feet, sort of defying gravity and again echoing that natural landscape. On the interior of the home, the natural underlying stone sometimes juts into the living space, while long bands of windows and glass doors allow for uninterrupted views that further unite the home with the surrounding landscape. Much of the stone used in the home's construction was collected from the surrounding countryside, and Wright also took a large boulder that the family used for sunbathing and transformed it into the central hearthstone of the interior fireplace. Even the unnatural concrete material was painted a soft beige or sand color to further unify it with the surrounding landscape. Reinforced concrete was really integral for breaking away from rectangular geometric designs. For example, Danish architect Jorn Utzon's Sydney Opera House is really a testament to the expressive character of reinforced concrete. Overlooking the harbor of Sydney, Australia, the roofline of the opera house resembles the billowing sails of a ship. These curved shapes were created over precast ribs and then set into place, allowing the architect more freedom in the design and, in theory, reducing the cost, although in this case, a series of unforeseen technical problems caused the project to cost 14 times its intended budget. Furthermore, there was a huge public debate over whether the design was beautiful and successful or a total monstrosity and a failure. And these combined controversies ultimately led Utzon to resign 9 years before the structure was completed. Beginning in the 1980s with a new approach to architecture that we now call postmodernism, form no longer follows function as it did in the modernist period. Some postmodern architects playfully combine elements from various historical, cultural, and regional styles to create new eclectic structures. For example, the Humana building in downtown Louisville, Kentucky includes a stylized post and lintel type facade that references classical Greek temples, but the upper portion of the structure has a series of curved surfaces that really flow or sort of undulate like the architecture of the 17th century Baroque era. The architect here, Michael Graves, he also varied the covering materials, changing the color and the texture at different intervals, giving the structure more ornamentation and creating greater visual interest. Many postmodern structures are playful explorations of the limitations of architectural design and of what we expect architecture to be, and they tend to incorporate more organic forms that can be quite difficult to visualize, plan, and achieve. However, the development of computer programs beginning in the 1970s and 80s has really allowed for digital design and fabrication techniques that can push architectural design to new heights. For example, Frank Gehry's Guggenheim Museum in Bilbao, Spain, was completed in 1997. The powerfully organic sculptural structure was designed to suggest ships and ship construction, reflecting the city's history as a center for shipbuilding and industry. Frank Gehry used computer programs that had been originally invented for aerospace design to plan buildings that contradict preconceived ideas about architecture and geometric forms. Most of the walls of the Bilbao Guggenheim consist of irregular, curving organic forms that rise and fall unpredictably. The undulating surfaces give a sense of movement and life to the structure, and the surfaces of these organic forms are then covered with titanium tiles that shimmer a brilliant silvery gold in the light. The interior space, which was designed to meet the changing needs of art and artists in the future, can be extended or reduced to accommodate exhibition needs. Additionally, the organic irregularity of the exterior continues inside. There are no strictly vertical walls or flat ceilings here. Instead, Gehry has molded and complicated the space. The main volume in the middle here sort of swells and bends to follow the lines of the structure. Some spaces are concave and some are convex, and each of the openings that surround this main space, which in this photograph we can see a balcony, a stairway, and a hallway, each of these sort of provides a different perspective on that central space and really invites us to sort of explore new and different areas of the museum.